Welcome to the UxART and UxART chapter of the HT32 MCU basic tutorial. Here is an introduction to the chapters in this tutorial. The first chapter, UxART Introduction, provides a simple introduction to help users understand UxART and UxART. The second chapter, UxART Architecture, introduces the function structure of UxART and UxART to help users understand the internal architecture. The third chapter, UxART Features, introduces the programmable communication functions of UxART and UxART, the supported modes, interrupts and PDMA settings and triggers. The fourth chapter, UxART Example, provides specific UxART configuration steps and application examples to help users understand how to use UxART. UxART Introduction. UxART and UxART are two communication interfaces. UxART stands for Universal Asynchronous Receiver Transmitter. It does not require a clock line, allowing communicate with fewer I/O pins. Two-wire unidirectional transmission uses TX for transmission and RX for reception, preventing bus contention. Transmission is possible at any time without the need for one side to initiate communication. UxART stands for Universal Synchronous Asynchronous Receiver Transmitter. In addition to having the UxART features, it can also retain the clock line to support the synchronous communication function. The basic communication modes of UxART and UxART are normal and synchronous master. In addition, Holtec MCUs support many communication modes, such as single wire, LIN, hardware flow control, IRDA, and RS-485. Actual support modes vary depending on the MCU devices. For details, refer to the user manual. UxART Architecture. Then, we'll introduce the UxART and UxART block diagram. UxART and UxART communication can be achieved by accessing the control and configuration registers via the APB interface. The baud rate clock generator is capable of dividing the UxART clock of CK UxART to generate a reference divisor clock for the transmitter and receiver by the baud rate divisor settings and CK UxART. During transmission, the hardware first writes the TX data to the transmit data register, then to the transmit shift register. The data is then converted into a TX byte under the reference divisor clock and is output via an I/O port. During reception, the RX byte is decoded into RX data under the reference divisor clock and stored in the receive shift register. It is then written into the receive data register. The system reads the receive data register to obtain the RX data. In addition, the UxART provides several interrupt signals to interrupt the system promptly for processing UxART operations. In the block diagram, the UxART replaces the transmit data register and receive data register with transmit FIFO and receive FIFO, adds the IRDA control function and RTS and CTS pins. The transmit FIFO and receive FIFO can cache larger amounts of data, meaning that interrupt can only be triggered once a specified threshold has been reached. This reduces the number of interrupts and prevents data loss due to delayed processing. The IRDA-EN allows the UxART to support the IRDA mode. The RTS and CTS pins allow the UxART to use the hardware flow control function to prevent transmitter overflow or receiver buffer overrun. UxART Features. For devices to communicate via UxART or UxART, both sides must use the same 5 configuration settings. The baud rate is defined as the number of bits transmitted per second and is used to determine the time interval for each bit. Common settings are 9600, 38400 and 115200 baud. The calculation method is as follows. As it is impossible to guarantee identical baud rates between different devices, a tolerance range of plus and minus 2.5% is permitted. The baud rate deviation is influenced by CK UxART. If higher precision is required, switching to an external clock source is recommended. Word length defines how many bits make up each word. Common options include 7, 8, and 9-bit. Stop bits defines the number of stop bits at the end of transmission. Common options include 1 or 2 bits. The length of the stop bits affects communication synchronization and stability. Parity. 5 parity modes are used to detect transmission errors. No parity. No parity check is used and this bit is removed. Mask. The parity bit is fixed at 1. Space. The parity bit is fixed at 0. Even. The parity bit is set to 1 when the sum of all the bits is odd. Odd. The parity bit is set to 1 when the sum of all bits is even. To ensure accurate data transmission, both communication interfaces must be configured with identical parameters. Mode is used to select the transfer mode. LSB, least significant bit, transmission begins with the least significant bit. For example, if the data is 0011, 0111, transmission begins with the rightmost one. MSB, most significant bit, transmission begins with the most significant bit. For example, if the data is 0011, 0111, transmission begins with the leftmost 0. The following specifications should be noted. 1. The baud rate clock frequency is up to FPCLK 8 Hz in synchronous mode. 2. The baud rate clock frequency is up to FPCLK 16 Hz in asynchronous mode. 3. The baud rate error must be less than plus or minus 2.5%. 4. Pay attention to voltage levels when connecting. 5. The output driving can be 4 or 8 or 12 or 16 mA. The following will introduce the communication protocol supported by the Holtec UxART. The first is the normal mode, which is the basic UxART function. The TX pin transmits a byte, and the RX pin receives it. Consequently, the TX and RX pins require cross-connection. Note that the voltage must be compatible with the MCU. This mode is typically used for one-device-to-one device communication. Next is the single-wire mode. This mode uses a single line for data transmission, enabling communication with a minimal I/O port. At the same time, a bus contention may occur. In this mode, the typical configuration is a master-slave setup, whereby the master finishes transmitting before the slave responds. In addition, adopting an open drain configuration for I/O settings and wiring prevents MCU burnout, even when transmitting data simultaneously. Next is the LIN mode. This is a widely used communication standard in the automotive sector. Its frame structure transmission enables an one master to multiple slaves architecture. A single valid transmission over LIN is termed a frame, comprising a header and a response. The header includes a break field with about 13 to 20 bits. A sync field, which is usually hex 55. And an identifier, which specifies the target slave ID. The response contains a data field comprising 1 to 8 bytes of data, and a checksum is used to verify the data bytes. During communication, the master transmits the header, and the slave with the matching ID responds with the response, thereby completing the communication. Both UxART and UxART support the aforementioned 3 modes. Next is the hardware flow control mode. As the UxART cannot determine the status of other devices, packet loss may occur in certain circumstances where the processing priority of the current device is higher. This mode uses RTS and CTS pins to achieve the hardware flow control. When the RX pin receives a byte and transmits it to the RDR register, the RTS signal will turn high until the RDR register is empty. If a FIFO level is configured, the RTS signal will also turn high when the RFIFO trigger level is reached. When the CTS signal turns high due to the RTS signal, the TX function is disabled. If the CTS signal turns high during transmission, the TX function will only be disabled after the current byte has been fully transmitted. Next is the IRDA mode. It is an infrared communication standard that enables wireless data transmission via infrared. The UxART signal is converted into pulse signal to drive the infrared transmitter for data transmission. The infrared receiver then receives the signal and converts it to UxART data. During signal conversion, a pulse is generated in the 0 bit of the TX data, as shown by the IRDA TX. When a pulse signal is received, the IRDA RX turns low. When the pulse is converted to data, the behavior is shown as the RX data. In addition, IRDA operates in two modes. In the normal mode, the pulse width is equal to 3/16 of the baud rate clock period. In low power mode, the pulse width is equal to 3 multiplied by IRDA PSC divided by CK UxART. Next is the RS-485 mode. It supports multi-master and multi-slave and is suitable for long-distance communication. During communication, the RS-485 transceiver converts signals into differential signals to minimize electromagnetic interference, and the RTS controls the transmission and reception functions. The device can operate in the auto direction mode as a master, which is responsible for transmitting commands. The device can operate in the normal multi-drop operation mode as a slave. When a byte with a parity bit of 1 is received, subsequent bytes are received continuously until the URRXEN bit is cleared by the software. The device can operate in the auto address detection operation mode as a slave. When a byte with a parity bit of 1 is received, check if the byte is a matching ID. If so, further bytes are received continuously until the software clears the URRXEN bit. Finally is the synchronous master mode. Before communication, select the communication device via the SC. During communication, the CTS pin outputs the communication clock signal while data is transmitted via the TX pin and received via the RX pin. Both signal changes and data acquisition rely on instantaneous transitions in the clock signal. This mode is typically used in SPI-type communication. Only UxART can support the subsequent 4 communication protocols. Now, let's learn about the interrupt and PDMA functions. Although the UART and UxART offer multiple ways of triggering interrupts, not every trigger requires an interrupt in applications. Consequently, the MCU can enable interrupts as required within the interrupt enable register. When an interrupt occurs, it is not possible for the software to determine its source. However, this information can be obtained via the status and interrupt register. If any of these 4 bits is set to 1, it means that an error occurred during transmission or reception. The OEI bit indicates data loss caused by buffer overrun. The PEI bit indicates parity error caused by incorrect byte data. The FEI bit indicates that the received character does not have a valid stop bit. This could mean that the transmission is incomplete or that the frame is faulty. The BII bit indicates that the start bit was received, but the remaining bits were lost. The UART control register can enable the RX or TX PDMA function. Once enabled, the PDMA function will execute when the RBR is not empty, the RX FIFO is equal to the threshold level, the TBR is empty, or the TX FIFO is less than the threshold level. UxART Example. Here, we provide an example to introduce how to use the UxART. We have chosen the interrupt example. Connect the UxART to a PC serial port, then use the terminal. In addition to the main program, this example also uses the UxART interrupt. We will introduce the main program firstly. After power on or restart, the system will execute the initialization. It then configures the data transfer and begins the transmission. Finally, it receives the data and transmits the received value when it receives a fixed value, repeating this process. The initialization steps are as follows. 1. Enable the IP clock. The AFIO is used to configure I/O pin functions, the GPIO is used to enable I/O pins, and the UxART is the IP that has been introduced in this tutorial. 2. Configure I/O. 3. Configure UxART mode with the following settings. Set the baud rate to 115,200. Set the word length to 8-bit. Set the stop bit to 1. Set the parity bit to none. 4. Enable and configure the required interrupts. Currently, only the RX function is required, so only enable the RX interrupt. 5. Enable the UxART Texas and RX pin function. Transfer setting 1 part steps are as follows. 1. Set the transfer data. 2. Enable the TX-related interrupts. 3. Wait until the transfer is complete. Receive data and transfer setting 2 part steps are as follows. 1. Wait until 5 bytes have been received. 2. Set the received data as the transmitted data. 3. Enable the TX-related interrupts. Following will introduce the interrupt. Interrupts can be categorized based on the interrupt trigger as follows. Receiving data, transferring data, and transfer end. When the flag indicates a receiving data, the system will receive and store data in an array. If the overflow protection is enabled, an infinite loop will be entered when the amount of data exceeds the storage capacity of the array. When the flag indicates a transferring data, the system will transmit data sequentially. Once the final data has been transmitted from the TDR, disable the TXDE interrupt. When the flag indicates a transfer end, entering this part means that the TSR is empty, which signifies that all data transfer is complete. Consequently, disable the TXDE interrupt and set the TXEND flag. This concludes the analysis of this example. This tutorial concludes with a list of the UxART and UxART APIs, along with their corresponding descriptions. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.